Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In a previous video, I talked about how you can define line integrals on an arbitrary manifold. In this video, what I want to do is define the notion of a surface integral. Now, when we defined line integrals, the things that we integrate was something called a one form. And it turns out to do a surface integral, we need a new concept again, and that thing is called a two form. Okay, so to motivate the definition of a surface integral, let's have a look and see what the definition of a surface integral is in a usual several variable calculus course. Okay, so we'll start with the surface, say S inside R3, and we'll parameterize this surface, okay, S inside R3. So what does that mean? So we'll consider some open connected set D, or domain, inside R2, and suppose the variables in R2 are U and V. And we have some sort of smooth map from D onto this surface S, and let's suppose it's injective. So this is going to give us a parameterization of the surface, parameterized in terms of the U and the V. Suppose the thing that you want to integrate is this F. So F is some vector field on R3. And one of the things that you need to do when you perform this surface integral is you need a normal vector. Okay, so in this surface S here, there's two normal vectors at any point. Okay, you can have one out like this, and the other one will point in the other direction. So what we'll do is we'll pick a direction based on the parameterization, and it's as follows. One way to get normal is you look at the tangent vector sigma u and sigma v. So sigma u is just the tangent vector that you get when you fix the v and you vary the u. Okay, so maybe it comes out like this. It's a tangent vector to S like that, sigma u. And then if you instead vary v and fix u, you'll get another tangent vector to that surface, sigma v. And of course, when you take the cross product of these two, you'll get a vector that's normal to this surface, and you can normalize it so that it's a unit normal. Okay? So of course, if you swap the u and v, you'll get the unit normal that points in the opposite direction. Now, once you've done that, you can define the integral of f dot n ds, so this surface integral here. And it's usually written like this. Okay? And it's quite easy to do that. What you do is you just basically pull back this to your domain here, and you perform a double integral in u and v. And what function of u and v do you integrate here? Well, as suggested by the notation here, you do f dot sigma u cross sigma v. So here, this will give you some vector in R3 for each point, and when you take the dot product, you'll get some function on this domain here. Okay, so that gives you the surface integral as you would see it in the several variable calculus course. So if you want to generalize this to manifolds, there are some remarks that we should make about this first. Okay, so what are they? So the first thing is that let's look back and think about what we did for line integrals. So the first thing is that when we did line integrals on an arbitrary manifold, what we integrated wasn't a vector field, but something called a covector field. So in other words, instead of something like a vector field f that we see here, it was the f and the dot. Okay, so there are things where the values no longer lie inside the tangent space, but in the cotangent space instead. Okay, so we similarly see f dot here. So really we want to concentrate on this f dot, and that's the type of object that we want to integrate. So that's the first remark, okay, A. The second remark here is that we need to orient this surface, okay? So there's a choice of orientation here, and it's very clearly important from this definition here. And in fact, we also needed to orient the curve for the line integral case, but orientations for curves are quite easy, because if you integrate along the curve, the orientation is which endpoint do you start at and which endpoint do you finish at. Okay, so it's very easy to say what the orientation is here for lines integrals. But for surface integrals, it's a little bit more complicated. So that's something that we'll need to keep in mind when we try to define surface integrals for manifolds. So that's point B. Remark C is that this definition is independent of the parameterization of x. Okay, so we picked a parameterization here, but you could have changed it. And the main thing is that you just want to talk about what is the integral over this surface. Okay, so you can change the parameterization in various ways, but if you change it in a way which keeps the orientation, this doesn't change here. Okay, so of course one silly way to change the parameterization is to swap u and v. And when you swap u and v, the only difference that you get here, of course, is this becomes the negative. Okay, so it's important that you keep the orientation when you reparameterize if you want the same answer. And that also emphasizes why the orientation is very important when you do surface integrals. Okay. The final point, and this is going to be the way we're going to try to think of things when we try to extend to arbitrary manifolds, is when you look at this integral here, I guess one way to think of it is as a Riemann sum, or limit of Riemann sums, rather. Okay, so what is this the limit of Riemann sums of? Okay, so you've got an f dot and you've got something here. So let's have a look at this part of the expression over here. Okay, so the key point that we want to make here is that that part of the expression, this sigma u cross sigma v du dv, you should think of as an infinitesimal surface element. Okay, so what do we mean by infinitesimal surface element? So let's have a look at our surface again here. And you've put coordinates on it, u and v, okay, through the parameterization. So you can consider a point with coordinates u and v. And then you can move out from u to u plus du. You can move out like that. Or you can fix the u and move from v to v plus dv. Or you can move both of them at the same time. So you can move out, at the end of the day, you'll sweep out something which is rectangular-like, and that is a surface element, okay, an infinitesimal surface element. And the key point is that this surface element has a certain area, okay, and that area can be approximated using this expression here, okay. So what you can do is you can approximate this segment here with sigma u du, this segment here with sigma v dv, and of course if you take the cross product of these two, you get the area of the corresponding parallelogram, okay, up to sine, that's what you get. So the magnitude will be that, but it also comes with a sign, okay, and the area of this parallelogram is going to approximate the area of this infinitesimal surface element here. Okay, we now come to the question of what types of objects are we integrating when we perform a surface integral? And the answer to that will be encoded in the notion of a two-form. Okay, so let's go back to our motivation, the usual surface integral that you see inside R3, and the integrand there was f dot sigma u cross sigma v. Okay, and remember the surface itself gives you sigma u and sigma v, so it's really this f dot which is the thing that we want to encode. Okay, so our definition for the two form will look fairly similar to how we did it for the one form. Okay, so a two form on a manifold X is what? So firstly, it's a type of function where you input for each point on the manifold X an object called omega p. So in the case of a one form, what this omega p was a covector. In other words, something in the dual space to the tangent space of X at p. Instead, what we want is a new type of object, which is in something called wedge 2 of t star px. Okay, so what type of object is this thing here? Okay, so let's look back and see what we have here. So before, for one forms, we looked at f dot and then some tangent vector. Here what's happening though is that we kind of input two tangent vectors, sigma u and sigma v. So what does f dot do? So if you give two tangent vectors, when you do f dot of that, that will give you some sort of a number. So that's the type of object that we want to integrate. Okay, so this set here, this omega p, is the set is going to belong to this set, and they're special types of functions L, where you input two tangent vectors v and w, and it spits out some number, some real number, L of vw. Okay, so that's the type of thing that we want to look at. So this two form though has to satisfy some extra properties. So before, when we looked at a one form, it had to be a linear functional on the tangent space, and so we're going to look at something similar here. Okay, so f dot of this pair of vectors, sigma u, sigma v, satisfies some special properties, okay? So firstly, if we look at the first vector here, this cross product is linear in both sigma u and sigma v. And the dot product is also linear in each variable. So it turns out this f dot, as a function of this sigma u and this sigma v, is both linear in sigma u and in sigma v. So we want this L to be linear in each of the variables v and w. The other thing that you'll realize is that if you swap sigma u and sigma v, this becomes its negative. So the value of f dot on that becomes its negative as well, because that's linear. So the other property that we want is that L of vw is equal to the negative of L of wv. So if you switch the order of these two, you get the negative. Okay? So an element of this wedge 2 of t star px is just a function which inputs two tangent vectors, spits out a number, and it does so in a way which is linear in each of these variables. And when you swap these two vectors, it goes to its negative. Okay, so what's the point about this? Okay, so why do we have this? So remember, what we really want is that this f dot just depends on this, this sigma u cross sigma v. Okay, it doesn't depend individually on the sigma u and the sigma v. It only depends on this cross product, whatever that happens to be. Okay, and this really represents this infinitesimal surface element. Okay, so how do you try to represent that? So the key point is that so if you have two vectors v and w, right, you really want it to represent this L to be a function just of the signed area of this parallelogram here. Okay, the signed area of the parallelogram that you get with sides parallel to v and to w. Okay, and so if you want to make that happen, you need both of these two properties to hold. And in fact, once you have those two properties to hold, then this L really just depends on this quantity here. Okay, so in other words, it captures the fact that it doesn't depend individually, it's not completely independent of the sigma u and the sigma v. Okay, it only depends on what the cross product would be. Okay, so that's why we have this definition here. And now that we have this definition, okay, if you're given such a two form, you can actually say what is the surface integral. Okay, so suppose you're given a surface. Okay, so that's some smooth map from some domain inside R2 onto some surface S inside our manifold X. Okay, then we can talk about what is the integral of omega, this two form, on this surface S. Okay, and this parametrization will give some sort of a orientation, so we don't need to worry about that. And the formula is just as we did before. Okay, so before we integrated this integrand, which is a function of u and v, so it's an integral over du and dv. And we'll do the similar sort of thing here. Okay, so the integral of this is, well, firstly, we integrate over u and v, so you can look at the tangent vector sigma u and sigma v for each u and v. Okay, and rather than doing the cross product here, what you do is, well, now for each point of d, right, you can look at L of this. Okay, so, or in this case, it's omega. So you evaluate omega at this pair of tangent vectors to get a number. So this is now just a function of u and v. And being a function of u and v, you can now integrate this. Okay. And as I said before, the key feature about this omega, these two properties here, mean that it only depends on the signed area of sigma u and sigma v. And that gives you the surface integral in this case, where the surface is parametrized. So what are some good examples of two forms? Well, recall that when we looked at line integrals, one way to get one forms was to consider a smooth function like f, and then we found one form was df. And what I claim now is that if instead you're given two smooth functions, f and g, we're going to get a new two form df wedge dg. Okay, so what's df wedge dg? Remember, this should be a function where if you input any point, what it gives you is one of these elements of this wedge 2 t star px. So in other words, you can input two tangent vectors v and w inside tpx, and it should spit out a number. Okay, so what number does it spit out in this case? So what we're going to do is we're going to form a 2 by 2 matrix and take the determinant of that. and that will be the number that we want. Okay, and it's quite easy to see what happens. Basically, we just let df and dg, okay, they're linear functionals on this tangent space, so they can eat up the v and the w as follows. Okay, so df, how does it eat up the v? So this is just the directional derivative along v of f, and then you can apply this directional derivative v in the direction v, dv of g here. And in the second row, we just use the directional derivatives of f and g, but in the direction of w instead. So dwf, dwg. Okay? And here, what you get is, of course, this is just some sort of a number. These are directional derivatives at the point P. So they'll be just numbers, and you'll get this as a number. Okay? And the things that you have to check now is, well, this has to be a function which is linear in both v and w. And also, when you swap these around, it should go to its negative. Okay, so let's check those properties. Okay, so if you swap v and w, what happens? Well, basically, the first row is the same as the second row, except for you've replaced v with w. So swapping v and w just swaps the two rows, and of course that just changes the sign of this determinant. Okay, so what about linearity in v? Well, of course, since you're just applying linear functionals on this v here, okay, so this is df of v and this is dg of v, of course, this first row is linear in v. And since this first row is linear in v, of course the determinant is linear in each of its rows. So this is also linear in v as well. And the same argument shows that this is in fact linear in w as well. So what we see now is that this does indeed define a two form. Okay? So once you have this two form, of course you can come up with lots and lots of other two forms. Okay, so you can scale each of these by some scalar, and you can do that by a different scalar at every point. In other words, you can multiply by a function. Okay, so if you have smooth functions fi, gi, and hi on x, you can in fact look at the sum of hi times dfi, which dgi. And that's something called a smooth two form, and they give you all the smooth two forms. And by using coordinates, you can simplify these expressions to a standard form as well. Okay, but that gives you already lots and lots of examples of two forms. And in fact, they're the ones that you want to have a look at. Okay, so far we've defined surface integrals, and we've assumed some sort of parametrization. And we haven't really looked at the orientation. We just sort of assume that the parametrization just gives you the orientation. So we need to consider the orientation now, and also remove the choice of the parametrization. So the fact is that the definition that I gave you for the surface integral is almost independent of the parametrization. Okay, it's almost independent, and there's only one problem, and it's a problem that we've mentioned before, and that of course is due to orientation. If you swap the u and the v, okay, then what happens in the integrand? So remember, in the integrand, what you integrate over u and v is this omega of sigma u, sigma v. So swapping u and v swaps these, and this goes to its negative. Okay, so that's basically the only problem. Okay, so what we're going to have to do, and this is something that we saw when we looked at the several variable calculus elementary version of surface integrals, is we have to record the orientation. Okay, so let's think about orientation. Let's go back to our usual surface integral inside R3. Okay, so suppose you have a surface like this, S. Okay, so then we have to choose your outward normal. Okay, so you have to choose an outward normal, maybe sticking out of the board or into the board like that. Of course, we want to do intrinsic geometry, and part of the point is that, well, if you use that as a definition, you need to stick outside the surface, so that's not intrinsic anymore, it's extrinsic, okay? So we need an intrinsic version of what that is. And the way we do that is using the right-hand rule, okay? So for example, if you want to stick out, that's also given by going around in the surface in a certain direction, okay? And what that certain direction does is it kind of orders this sigma u and the sigma v, okay? So if you've got coordinates here, say u and the v like this, right? Then going around this direction means that you go firstly from the positive u axis to the positive v axis secondly. So it orders them, okay? If you make the direction go the other way, okay, that's supposed to represent in your elementary surface integrals in R3 case, the normal going into the board, then you go around like this, so that means that the positive v axis goes first and the positive u axis goes second, okay? So that's one way that you can record orientation. Okay. So the question is, how do we factor this in when we just want to integrate a surface? Okay. And let's suppose that there's no preferred parameterization. Okay. So suppose we're given a smooth surface S inside X. Okay. So of course, if it's a smooth surface, it's a surface, so it has chart. Okay. So let's suppose the chart is given as follows by these phi i's, and they're going to be homeomorphisms from the unit balls of dimension 2, so these unit disks, BI2, to open subsets VI inside our surface S. And the key point is that if you want to do a surface integral, I guess you can use all these charts to do this surface integral. Okay, so this gives you a parameterization of at least part of the surface, so you can do the integral there. Okay, and of course this comes with an orientation. And the most important thing is, how do you check that the orientation of one of these charts matches up with the orientation on another chart, so that you don't have the the orientations differing in this sense, one going one way and the other one going the other way. And the answer to that is quite easy. Okay, so what you want to do is you look at the transition functions. Okay, that's the way you move from one chart to another. Okay, so the transition function, let's look at tau ij, which goes from bi2 by applying the phi I, and then you apply phi j inverse back to some open subset of bj. So this goes from bi to bj, so some open subset of r2 to some open subset of r2. And what you want for these charts to be oriented is that that's an orientation preserving map in the following sense. So what does it mean to be orientation preserving? Okay, so at the end of the day, this is just a function from an open subset of R2 to an open subset of R2. Okay, so you can look at the derivative of this. Okay, and then you can look at the derivative at every point. Okay, and that's just going to be some 2 by 2 matrix. Okay, and you can ask the determinant of that is always going to be positive. Okay, so remember, this is going to be a smooth with smooth inverse, so the determinant has to be non-zero. And the point is, to be orientation preserving means that you also want not just that the determinant is non-zero, but the determinant is positive. Okay, and that makes sure that when you try to perform the surface integrals, it doesn't matter whether you use phi and phi j. If you're integrating on the intersection of vi and vj, it doesn't matter which of those that you use, you'll get the same answer. Okay, and because of that, that means that now you can use that definition too, and these charts to define this integral here. Okay, so that's the point. And of course, the key point is that these charts will induce an orientation on this surface S on VI, and it doesn't matter which chart you use, they'll give you the same orientation, and hence an orientation on all of S. I hope you enjoyed this adventure in pure mathematics.